Hey class, welcome back to Behavioral Statistics. We are moving into our 10th chapter of the course. This is kind of part two on t-tests. We looked at the basics of t-tests in chapter 9. We'll look at independent samples for chapter 10, then repeated measures for chapter 11. So it's kind of its own little subsection within obviously the course. We're going to be looking at t-tests for two independent samples and going over that. So the learning outcomes will be by the time this chapter is over, you should be able to understand the structure of research studies that are appropriate for using independent measures, T hypothesis test the difference between two populations or two treatments using independent measures, T statistic, and then you're going to evaluate the magnitude of the observed mean difference or effect size using Cohen's d, R squared, and or a confidence interval, and then understand how to evaluate the assumptions underlying the test, your independent samples T test, and how to adjust calculations when needed. So some things you're going to be using from previous chapter, sample variance from chapter 4, standard error formulas from chapter 7, and then obviously we're talking about T statistic, a new type of T statistic or a different way of conceptualizing it. So we're going to be dropping back into chapter 9. T distribution values. So you're going to be using that T chart, degrees of freedom for the T statistic, and then also your estimated standard error, so that denominator of the T equation. So when it comes to understanding kind of the time and place of when to use an independent measures design, we need to look at, when we talk about research models, most research studies compare two or more sets of data. So you have kind of two kind of broad categories that could fall under data from two completely different independent sample or participant groups. This is considered an independent measure or between subjects design. So an example of this might be sleep deprivation. So how does that impact cognitive performances? And you have two independent groups. So you might be comparing college students who range from the ages 18 to 25 and an older adults who maybe are 60 and up. So they're independent. Their observations are independent of each other. When they both are completing maybe cognitive performance assessments, an 18-year-old taking their assessment has no impact on a 60-year-old taking that same assessment and vice versa. And then we can compare the results. There's also data from same or related participant groups. This is called within subjects design or repeated measures. So this is when maybe instead of using two different groups, so now for maybe we're interested in sleep deprivation. Oh, excuse me, I'm getting a call real quick from my wife, so I'm gonna pause this just real quick. Oh, hey baby. Uh, yeah, I was recording something, but I paused it. Okay, can I call you back when I'm done? No problem. Bye. Okay, I have no idea if that it said stop sharing or pause sharing. I don't know if it paused the recording or not. But anyways, so welcome back. Thanks for your patience if you did have to sit through. I'll call my wife back after I'm done recording this. So these are just kind of the two broad kind of categories for research when we're talking about comparative research, comparing means, for example. So when we talk about the independent measures design, typically there are two different designs. Each has its own kind of strengths and weaknesses. But really, the between subjects are designed are considered in this chapter. So we're talking about those that measure maybe where we're comparing college students with older adult. We're comparing two populations. Next chapter, we'll get more into those repeated measures designs. Okay, so essentially what we're talking about here is maybe we have a population. Again, it could be college students and it could be older adults. We're going to draw a sample from both of those, and then we're going to compare those two samples. So, two separate samples are used to obtain the information about two unknown populations or treatments. This is kind of a visual way of understanding what's going on here. And so, if we're coming up with hypotheses for a independent measure, our null hypothesis is saying there's no difference between our populations. So when we subtract our mean, our first mean from our second mean, so this could be subtracting our older adults from our college students, that's going to come out to equal zero in terms of the mean difference. Our alternative hypothesis, on the other hand, is an independent for the independent test is there is some kind of mean difference, meaning it will not equal zero. Maybe one group scores higher, one group scores lower in this case. But that's now this of course I shouldn't use that language because this is referring to a non-directional hypothesis here. If we talk about lesser or greater, then obviously we're getting into a directional hypothesis. So apologies if that was confusing at all. But here's the basic structure of the t-test. Essentially, what we're going to do, the basic structure, is we're going to take our sample statistic minus our hypothesized parameter divided by the estimated standard error, our numerator. So this is pretty, similar to the t-test, the formula you all looked at last week, but now we're just expanding it. We are expanding it just a little bit. We're now adding in a second sample. We have more than one sample statistic that we're going to take a look at. So this is a formula that I would have handy and ready, when you're putting your notes together, if you're putting a cheat sheet together, things like that, this would be a good formula to have. And in terms of finding that, so this we're just using the means, the sample statistic to find these. In order to find the denominator, the estimated standard error for the denominator, we use this formula below. We use our standard deviation for sample one, standard deviation for sample two, over the total number of participants, their sample size one, sample size two, and that's all going to get square rooted. So what we're trying to look at is how much of a difference is reasonable to expect between two sample means if the null hypothesis is true. So kind of some mathematical background about that. You might be wondering why add sample measurement errors, the square deviations from the mean, but subtract sample means to calculate a different source. I'm not like I use these statistics, but I'm not like the math whiz to understand behind it. But the logic behind this is that like the variability for the differences in scores is found in adding the variability for each of the two populations. So just kind of opening up the hood and maybe explaining a little bit of what's going on with that particular formula. So again, we might want to compare populations. We might have population one versus population two, and this is just a visual depiction of that. We have two population distributions. The score in population one ranges from 50 to 70, a 20-point spread, and the score in population two ranges from 20 to 30, a 10-point spread. So we can see population one has more variability. It's scoring higher, but has more variability. If you select one score from each of these two populations, the closest two values are X1, which is 50, and X2, which is 30. The two values that are farthest apart are X1 are 70 and X2 20. So a 50-point difference there. And so we're able to kind of take that into consideration when looking at that numerator. Okay, so also consideration of pooled variance, equation 10.1. So if we go back, 10.1 is right. I'm assuming they're referring to this one, sorry. Or maybe they're referring to this one. Yeah, this one, sorry. For 10.1, here we go. This is an unbiased only if the two samples are exactly the same size. So we have equal sample size. Pooled variance, though, provides an unbiased for calculating standard error if we don't have those. In that case, we use sum of squares plus sum of squares one for our first sample, sum of squares for our second sample, divided by degrees of freedom for first sample plus degrees of freedom for second sample. So this numerator might look a little different depending on what we know or don't know about our data. So the estimated standard error, mean one minus mean two, is the calculated using the pooled variance. So you can do it this way for estimated standard error. The independent sample statistic for finding the degrees of freedom is your sample mean difference minus population mean divided by standard estimate. And to use degrees of freedom, we go of our first sample plus our degrees of freedom for the second sample. So that's going to be N1, sample one minus one. So if we had 20 participants in our first sample, we would go 20 minus one plus, and let's say we had 20 in the second sample, 20 minus one again, add those together, and that gives us our degrees of freedom. And that's what you use to look up on that chart. You use your probability value, your p-value, and then you use degrees of freedom. Okay, let's do a quick learning comprehension check. Which combination of factors is most likely to produce a significant value for an independent measure's t-statistic? Is it A, small mean difference and small sample variances? B, large mean difference and large sample variances? C, a small mean difference and large sample variance? Or D, a large mean difference and a small sample variances? Go ahead and pause the video here. Think about this, maybe write out your answer or type it up in your notes or somewhere. Make sure you understand, what the answer is and why before moving on. Go ahead and pause now. Okay, I'll assume you've paused and you're coming back. In this case, the answer is D. We're looking for bigger differences in our means. I mean, if you go back to that formula, if you go back to the formula itself, oop, here it is. Wait, sorry. Where's the formula? This one here. The bigger the differences our means are, the stronger the bigger our numerator is going to be, and the smaller the variance, the smaller our denominator will be. So just kind of mathematically, it makes sense when when the mean difference is high, small sample variance is low, we're more likely to get those higher t statistics, which means we're more likely to get significant results. So hopefully that makes sense. If it doesn't, please ask, please send questions. Okay, next one. If both samples, so true or false, if both samples have n equals 10, the independent measures t statistic will have degrees of freedom of 19. And then second one, true or false, for an independent measures t statistic, the estimated standard error measures how much difference is reasonable to expect. The sample means if there is no treatment effect. So go ahead and same thing, pause the video here, make sure you understand before moving forward. Um, and then unpause the video, come back, and we'll reveal the answers. Okay. First one is false. And the degrees of freedom formula for the independent samples, remember it's N1, so that's sample one minus one plus sample two minus one. So if they both had 10, in this case, we would be going 10 minus one, that's 9, plus 10 minus one, that's 9. Add those together, that's 18. So it wouldn't be 19, it would be 18. And then this is just an accurate, second one is true. This is an accurate description. This is just the definition of what we're using our standard error measure. Okay, hypothesis tests with our independent measures. Typically, we have those four steps that we've talked about already. We talked about those with Z of X bar tests. We talked about those with our T statistic. Same thing we're talking about with the independent measures T statistic. We want to state our hypotheses, our alternative, or excuse me, our null and alternative hypotheses. Select the corresponding alpha. For most things in the social sciences, you're going to be talking about 0.05, so that's kind of a given for you. You're going to locate those critical regions using that t-test handout I gave you, and then obtain the data, compute your t-statistic, so running through that formula, and then you make a decision. Do we reject the null hypothesis, or do we fail to reject the null hypothesis? So those four steps, I would sequentially go through those four steps. I would draw out your t-statistic, or excuse me, your normal distribution, just to have that visual element. So this is what I mean. If we have a hypothesis test, we're running it. We're going to run a two-tailed non-directional test. We have 14 degrees of freedom equals 14. So our critical region is going to be negative 2.145 on the left side, positive 2.145 on the right-hand side. If we calculate our t statistic and the value falls to the left over here or to the right over here, then we can reject the null hypothesis. If we run the t statistic and everything falls in the middle here, then we can't. We fail to reject the null hypothesis. Or we retain the null hypothesis, however you want to say it. So typically we are talking about non-directional. You can use directional hypotheses when you're predicting a specific direction for the difference and it's justified. Like you have a reason why you think the difference is there. You would locate the critical region in that appropriate tail, the left or the right hand side, and then you would also, in terms of the data you report, maybe in a journal or to a conference or a presentation or whatever, you would report the use of a one-tailed test explicitly in your research report. You might write it up as such. You would say T with degrees of 14. This is our T statistic, gave us 2.67 with a p-value that is less than 0.01, and you would indicate with a comma that this is a one-tailed test. This is a directional test. Okay, so some of the assumptions underlying our t statistic, that's kind of one of the things with all of these tests for hypothesis making or decision making. We have assumptions we have to meet. So one, the observations within each sample must be independent, meaning one participant's score or response does not impact somebody else's. So back to the original example, somebody who's in that younger adult college student taking their cognitive assessment compared to an older adult 60 or above, their measurement, how they take that survey about cognitive assessment, does not they're not they do not impact each other. Next one, the two populations from the sample are selected must be normal. We're talking about the normal distribution of our populations. They'll have that normal shape. The two populations from which the samples are selected must have equal variances. This is the assumption of called homogeneity of variance. So there are a statistical tests that you would actually run to test this last sample. It's called Hartley's F max test. You're testing for homogeneity of variance, and it's your variance of your largest over the square root of your largest square root your standard deviation largest over your standard deviation smallest. The larger value indicates a large difference between your sample variances, which indicates you might be violating that assumption. A smaller value, which is closer to one, indicates that our similar sample variances and that the homogeneity assumption is reasonable. The variances are reasonably equal. If our sample information suggests a violation, you can calculate the standard error with 10.1. You would adjust the degrees of freedom for the test for your t-test. Instead, you would use this sample instead, which is a heck of a lot more complicated. But if we violate that homogeneity of variance assumption, we have to kind of follow another step using this equation here. So our degrees of freedom are going to look much different. Okay, so other things we can do, we can measure the effect size in terms of confidence intervals or Cohen's d, or we can even look at the percent of variance through R squared. So if our null hypothesis is rejected, we can look at the effect size using Cohen's d, our estimated mean difference over our estimated standard deviation. So that's M1 mean 1 minus mean 2 over our estimated standard deviation. And then you could also do the percentage of variance. You can take R squared, which just takes your t value, your t score, square that, divide that by t squared plus degrees of freedom. So that'll tell us how much of our variance is actually explained by our intervention in this case. There's also the confidence intervals that we can create. We can take our sample mean difference back into our equation. We can just rearrange this equation to create our confidence intervals, which again, remember, our confidence intervals are just a range of values that we think, we can estimate. We're pretty certain that our mean, remember, because we're going from population mean to sample mean, we are not 100% certain, but through confidence intervals, specifically using like those 95% confidence intervals, we can be pretty sure where the data would fall. We may not be 100% sure, but we can be pretty confident. So what these can do is with confidence intervals, it provides us an indication of the size of the treatment effect and can provide an indication of the significance of that effect. And if the interval contains zero, so that range, then it is not a significant effect. So when you're creating those confidence intervals, you're looking for things that do not contain a zero value. If the interval does not contain zero, the treatment effect was significant in this case. So here's kind of a visualization of that. We have a confidence interval, our mean difference. We have a confidence interval of 0.782 all the way to 7.218. And then our null hypothesis would say there's no difference, but we look at this, the 95% confidence interval for the population mean difference, for example, 10.6. Note that our mean 1 minus mean 2 equals 0 is excluded from the confidence interval, indicating that a zero difference is not an acceptable variable. In this case, our null hypothesis would be rejected using a zero point 0.05 alpha. Okay, reporting those measures, reporting your results of an independent measures t-test. You can report whether the differences between the groups are significant. You can report descriptive statistics like mean and standard deviation. You can report the t-statistic plus the degrees of value, p-value, and also your confidence interval like the previous example. Those are all things being generated for you. Now, obviously, we've gone over the math and how to create those things, but when you're running a program like SPSS, for example, it'll actually compute all of that for you. So other things to consider: the role of sample variance and sample size in your independent measures t-test. Standard error is related to sample variance, so how much variance there is amongst your sample from population. Larger variances lead to larger error. It can also lead to a smaller value of t, making it closer to zero, and reduce the likelihood of finding a significant result. And because larger samples produce smaller error, larger samples lead to a larger value for the t statistic. So kind of showing you where things like sample size and variance factor in to that t statistic measurement. And here's a variation here. We can actually see treatment one, treatment two. We can clearly see treatment two performed better. The two sample distributions representing two different treatments. These data show a significant difference between treatments. T of 16, of degrees of freedom 16, 8.62. P is less than 0.01, and both measures of effect size, a large treatment effect. We have degrees of freedom Cohen's d equals 4.10, and R squared equals 0.82. So this is maybe just how you might visualize that representation. And here's another example. The two sample variations, they're different treatments. So we have treatment one, treatment two. They have same variance, same sample size, but different means, of course. Show exactly the same mean difference as the score in 10.5. However, the variance has been greatly increased. With increased variance, there's no longer a significant difference between the treatments. So when we increase the variance, just kind of showing you again what variance does to the likelihood of finding a significant result. Okay, let's do a couple more learning checks. For an independent measures research study, the value of Cohen's D helps to describe what? Is it A, risk of type 1 error, B, risk of type 2 error, C, how much difference there is between the two treatments, D, whether the difference between the two treatments is likely to have occurred by chance. Go ahead and pause the video here, write your answer down, make sure you understand. All right, hopefully you pause and you're back. Correct answer is C. We're looking at how much difference there is between the two treatments. That's how much we're not only looking at is there a difference, but what magnitude, how much of a difference is there. Next one, true or false. Homogeneity assumption requires two sample variances to be equal. And second one, true or false, if a researcher reports that our T score of degrees of freedom 6 equals 1.98, p-value is greater than 0.05, then the null hypothesis was rejected. Go ahead and pause your video here. Make sure you understand both of these before moving on. Okay, both are false in this case. The first one is false. The assumption requires equal population variances, but the test is valid if sample variances are similar. So requires sample variances to be equal, but population variances, but if sample variances are similar. Okay, and then next one, our null hypothesis is rejected when p is less than 0.05 and t is greater than the critical value of our t. Okay. And here's what an output would look like in SPSS. You would have your means for your two groups, your variables. So group one, group two, mean one, mean two. Here's our variance. Here's our standard error of the mean. We can test for significance, variance is assuming variance is not assumed. Yeah, and we can clearly see, yeah, we can see what's going on here. We can see this is a significant result. So, anyways, that is it. This is the kind of this is the kind of t-test you would use for comparing two independent samples. I'll see you on the other side. Please let me know if you have questions. Otherwise, I'll see you all on the other side for chapter 11. Take care. Bye.